So welcome everyone. Today we have Lasse Knudsen here. Lasse is a postdoc at CMR working on the 10.5 Tesla with Luca Vizioli. And some of you know Lasse already. He has been a Laminaut since maybe 5 years or so. When he was starting to do some layer fMRI also with the Vaso sequence in Denmark. I think Lasse is most known for his layer fMRI, also layer fMRI Bolt at 3 Tesla, but also from his work doing optimization work for Nordic denoising for 3 Tesla Vaso, but also 7 Tesla Vaso. Lasse has been using layer fMRI also in patients, ALS patients, I think in collaboration with the Chinese Academy of Science, if I'm not mistaken, where you did your first postdoc for a short time now. Since a year or so, or longer than a year, you're already at CMR, and you're going to show us the latest, coolest high-resolution fMRI from 10.5. Yeah, please
Right.
go ahead and share your screen.
All right. Thanks, Renzo. Let's see here. Does that work?
Yes.
All right. Well, let me get right up this. All right. Yeah, thanks for the presentation or the introduction, Renzo, and thanks for allowing me to present this data here at the seminar. So yeah, I'm Lasse. Hello, everyone. The title is gonna be of the presentation is Bridging the Gap with Invasive Imaging, Promises and Challenges of a New Generation of Ultra-High Resolution fMRI. And the center of this talk is gonna be the main work that I've been doing here at CMR since I arrived like a year ago, which can be summarized as I would say, a contribution to the efforts of doing 0.35 millimeter isotropic functional imaging at the 10.5 Tesla scanner at CMR. And by the way, the data that I'm going to show here, we just submitted that to bioRxiv on Friday. So unfortunately, I can't put the link yet here, but it should be out there in a couple of days or so if anyone is interested. All right. So I asked this question, right? Ultra high resolution, why bother? Like, why do we want to go to and move to 0.35? It's hard. There's a lot of challenges involved. Why do we want to bother? And I do realize that this might be kind of an obsolete question in this audience. I mean, most of us are probably very fond of resolution. We are hungry for it. We want everything that we can get, right? But I'll anyway go ahead and present this example, which is my favorite, that very clearly shows to me and excites me about why we want to bother, basically. So this is work by Andrew Pesicchetti and Renzo was also involved, where they're looking at M1, and then M1 can be divided into these superficial layers, which is the input layers where motor planning from other regions of the brain is being sent to. And then there is the deep output layers, which is where the corticospinal motor output neurons are located, those that sense the motor output to the spinal cord. And then they're comparing these two different tasks here. So there's a imaginary task where people are just thinking about doing a finger movement. And then they compare that to this other task, which is actual finger tapping. So where subjects are moving their fingers. And then when they compare these two tasks at like very old school, low resolution 3 millimeter scans, then there's absolutely no difference. Like the spatial pattern is 1-to-1 the same, right? Which is probably not very representative of what's actually going on in the brain. But then once they study these same tasks, but after pushing to, in this case, around 0.7 millimeter resolution, then things change and you start to see different things. So in this imagined task, where there's no actual movement, you only see a superficial stripe in line with motor planning input coming to the superficial layers, but no motor output because there's no hand movement. And then for the actual finger tapping task, there is movement and therefore motor output, and therefore this deep layer stripe here also appears, which I think this is just cool, and it tells me all I need to know, that when we start pushing the resolution, we start seeing things that we could just otherwise not see. and we get a better understanding of what's actually going on in the brain. This is obviously just one study among now a big body of literature that has like gained more information by enabling this extra dimension of the cortical layers, right? By pushing to sub-millimeter resolution. The thing though is that considering that we have these 6 histological layers that are spanning a cortical thickness of around 1 to 3 millimeters, at least out in most brain regions outside of M1, then it becomes apparent how the 0.8 millimeter isotropic resolution, which is sort of the standard in the field now, might not be enough to capture subtle modulations across the cortical ribbon. Like there's probably more information to be gained by pushing even further and have less partial volume across these layers. And a nice example of that is this is data from the Fine-Bergertron scanner. So this is vaso data being acquired at 0.4 millimeter isotropic or 0.39. And you see here that at these resolutions, you can clearly see nice distinct peaks, one in superficial layers and one that corresponds to layer 4 for this visual task in V1. And then once they start downsampling this data, more and more you see the peaks quickly sort of disappears and blurs away. And once you get to 0.8 millimeter isotropic, then it's basically completely gone, and you get one big blob extending across all layers, and you basically get the wrong idea about what's happening in the cortex for this task. So this was recognized by the NIH Brain Initiative, which has pushed for spatial resolutions going beyond 0.01 microliter voxel volumes in humans. And how do we get there then? Like, we know that when we push resolution, we get into trouble with SNR, and that can become a limitation. But one way of dealing with that is to move towards higher field strength, which has this nice effect that it provides a supralinear boost for bold functional contrast to noise ratio. So by moving to higher field strength, you both get the benefit of more signal, higher SNR, but at the same time, the bold effect itself, the effect size, is also scaling with field strength. And so combining those two factors, the dependence of functional contrast to noise becomes supralinear with magnetic field. So that certainly helps to overcome the SNR limitation. Another thing we can do is using Nordic denoising, which in this case, this is from our 0.35 millimeter acquisitions, where you see a lot of thermal noise without Nordic, which is the dominant source of noise in this regime. And then after Nordic denoising, a lot of that has been nicely suppressed, and we get high image SNR. Another advantage, obviously, from moving to higher fields when using gradient echo bold is that we get a higher microvascular weighting. So we get relatively more sensitive to the capillaries that are close to the neuronal activation of interest. And we get relatively less sensitive to these large peel veins at the cortical surface that drains away the signal, basically, and gives us spatial mislocalization of the neuronal activation. And so by moving to higher fields, we can get away from something, maps like these. This is now a 3 Tesla activation map, where you see that most of the bold activation is towards the surface or even in the CSF towards these veins here. So this has certainly been a popular strategy in the field. Like the vast majority of studies of layer fMRI studies have been performed at ultra high field systems, so 7 Tesla or higher. And that's despite the fact that there are obviously much fewer of those ultra high field systems worldwide. And now there are also efforts to push the field strength even further. So these are the ones I'm aware of, examples that I'm aware of where people are trying to push the field strength even beyond 10 Tesla. So some of these are operational already, some are still under development. But this scanner here, the 10.5 Tesla at CMR, is operational, and that's the one we have been using to acquire the data that I'm going to show in this talk. So what we did here is we tried to use this high field to acquire functional images with gradient Ugurbil at 0.35 millimeter isotropic, which corresponds to a 12-fold improvement in voxel volume relative to the 0.8 standard. So that's quite a huge improvement in resolution, and we're trying to use that to move towards resolving individual layers, right? That's the ultimate goal. Eventually, is to be able to resolve activation from each individual histological layer. And at conventional layer resolutions, even we're not really close to that, right? We're limited to interpreting our laminar profiles in, like, for example, in these like broad scale groupings of the layers. So for example, superficial versus deep. But by pushing the resolution like this, we're trying to move towards that goal. And the model system that we're using here is layer 4 in V1. So we're trying to see if we can resolve the expected activation peak based on electrophysiology at layer 4 during low-level visual stimulation. And this has been resolved previously in the animal model. So this is monkey data from Guernsey, where you can clearly see here there's a very nice and distinct peak here in the middle layers. And how do we know this then corresponds to layer 4? Well, if you zoom in on this anatomical, high resolution anatomical scan up here, then you can see this this line here of lower signal intensities that is traversing the middle of the cortex, which is the stria of Gennari in V1, which is this highly myelinated band that traverses layer 4 of V1 specifically. And when you plot the intensity profile of this image, it looks like this. And this little dip that you can see here in T2 star weighted intensities is the stria of Gennari, which aligns with its peak and tells you, okay, this is layer 4. So it has also very recently been nicely resolved in humans using non-gradient Ugurbil DPI. So in this case, it's basal. And this is the data that I showed you before in the downsampling example. So here they are at 0.39 millimeter isotropic, so very close to what we did here with gradient Ugurbil. And at those resolutions, you can clearly see these distinct peaks, one of them being above layer 4 as expected. This is also visual, this is also checkerboard stimulation. So low-level visual stimulation. Then if you do that same experiment, but you do it still with basal and high spatial specificity, but now at 0.8 millimeter resolution, then the profile, it obviously still peaks away from the surface towards the middle layers, but it becomes much more fuzzy, much less distinct. And with gradient Ugurbil at those resolutions, it's worse, right? Like it just this ramping profile, and you don't see a peak here towards the middle layers. So very recently, however, we put this data on bioRxiv, where so this is first authored by Luca, and this is where we did 0.35 millimeter functional acquisitions with gradient Ugurbil, and we did that at 10.5 Tesla. And you then see that in all 4 subjects here that we scanned, we can see a clear activation peak at the center of the cortex, and that nicely aligns with our T2 star weighted profiles that are shown here above. And not only do we see this stria dip, by the way, in the anatomical profiles, high resolution profiles, we also see that directly in the functional, when we plot the mini PI profile in that same RI. And to me, that's quite cool that we can, based on the functional data itself, we can use that to localize what is the peak that we're actually looking at here. Which layer does that correspond to? So yeah, this is an example that, again, that by pushing to higher and higher resolutions, we start seeing things even with gradient echo bold that was just not visible before. Like here, when we compare to the 7 Tesla case, that's the blue profiles at 0.8 resolution. Then it's again mainly this ramping profile without a clear, distinct peak at the middle layers. So what we wanted to do here in this study is we first wanted to replicate this observation that we can resolve the layer 4 functional peak that co-localizes with this stria dip, identifying layer 4. And then on top of that, we wanted to go into more highlight and discuss some of the challenges that arise in this regime, because it is kind of hard to deal with these, both the field strength and the resolution at ultra high scales. So
Lasse, can I ask you something about this last plot? So you're comparing 10.5 and 70, but then also you said something about the resolution. So the blue and the red are not the same resolution. So there's different field strength and different resolutions.
Yes, exactly.
Gotcha. Okay, makes sense. Makes sense.
So it's 0.8, 70 versus 0.35, 10.5. Yes.
Gotcha. Thanks.
All right. So these are the sequences that we used. So we have our anatomical sequence at 0.37 millimeter isotropic, which was a 3D multi-echo gradient echo sequence with a flash readout. And this was whole brain. And then we had a 0.35 millimeter isotropic functional scans, which was 3D gradient echo API with a VAT, or volume acquisition time, of around 5 seconds. And then we got 40 coronal slices. And then in one subject, to provide like a reference for a more conventional laminar fMRI setup, we got this 7 Tesla 0.8 millimeter acquisition, in this case using a 2D gradient echo API acquisition. And here are the images, the high resolution images from 10.5 Tesla. You can appreciate the data quality. And if we zoom into the back part of the brain, so the primary visual cortex, you can clearly see this stripe here of low intensity values that is traversing the middle of the cortex. So again, this stria of Gennari, which you not only see in the anatomical image, you can also very clearly see it in the functional scans. And again, this shows up in the profile as this dip here, so we know where layer 4 is at. Then I also wanted to show here that, so this is now an axial slice, right, where we also clearly see the stria in the mean EPI, but after Nordic denoising and by being at this high field strength, we have the SNR in the single volume EPIs to also see the stria very clearly here, which I think is quite cool. All right, so that higher image SNR also translates into robust activation. So this is the activation we see to only 15 minutes of checkerboard stimulation block design. So it would be blocks of these flashing checkerboards alternating with fixation blocks. And not only is it robust, it also seems quite specific. So it nicely follows the cortical ribbon here, the activation. And the blue arrows point to locations where we can clearly separate the activation across 2 adjacent banks across the sulcus, which is not trivial with gradient echo bold. So here I'm showing more examples. This is the same as above here, just in other data sets, now just with green arrows instead of blue, pointing to these regions. But then when you compare it to the 0.8 millimeter case, again at 7 Tesla, then you don't really get that separation, which is probably a partial voluming effect, but it's also, I think, a specificity effect, since the activation is now just, it's one big blob that sort of peaks in between the 2 banks. So basically in the CSF or towards the superficial layers, and we don't get that nice separation anymore. And again, this is, we believe, probably a field strength effect that gives us higher microvascular weighting, like I mentioned before. But it might also be another effect, which was described nicely by Kamil in 2016 and 21 papers, which is a resolution effect for specificity. So I'll try to illustrate that here. And the idea is that if you have a large vein like this in an inactivated state, where there's a lot of deoxyhemoglobin, then around that vein there'll be some field perturbation, right, which can be appreciated by a Faes image like this. And then the idea is that when the voxel becomes small enough and approaches the scale where those field inhomogeneities like approaches that same scale, then the variation in magnetic field across the voxel will be relatively small. And so the defacing inside of the voxel, that is the Bold effect, that gives rise to the Bold effect, that will be suppressed. And that happens when this effect sort of kicks in when the voxel approaches the size of the vein itself that is giving rise to those field perturbations. And that is the case at 0.35 with respect to the largest of the PL veins in humans that are at the cortical surface. So some of the suppression we see down here of that CSF signal might also be due to this resolution effect. But again, like Renzo just pointed out, this is both a resolution and a field strength difference in those two maps. And so we cannot really tell the relative contribution of those, but this is something we want to look more into. Here you see the laminar profiles. So this is now 4 new data sets that compared to those you saw from Luca's paper. But also in all of these, we see that we can identify this peak here at the middle layers, which nicely corresponds or co-localizes with the dip in the mini PI profile. And this peak activation here at the above the stria can also be visualized directly in the activation maps using some within layer smoothing here, which I implemented with Laney. And so here we have 2 different subjects that were scanned in 2 different sessions. And then we replicate this feature that we can see a stripe of activation here, which nicely falls on top of the stria, which is highlighted here by these blue circles. Then again, when we compare to the 0.8 case at 7 Tesla, then we see a lot of activation, like it's very robust and strong, but a lot of that activation is coming from from these large PL veins. So it's not super specific. And when we then compare the maps directly, again, within layer smooth, then we see that in the 0.35 millimeter data, we can see this stripe of activation following the stria, which is not the case at 0.8. And when we look at the profile, it's reminiscent of those we saw before, where it's a ramping basically towards the superficial layers, and there's no distinct peak at the middle. And we also don't have the resolution at 0.8 to visualize the dip in the stria that identifies layer 4. So we were quite excited about being able to replicate this. Like it seems that this, like the ability to resolve this layer 4 peak is quite robust across subjects. And so following this, I'll now switch gears a little bit and highlight some of the challenges that are involved in getting here in imaging at these resolutions and field strength. So the first challenge is that of layer positioning, which I define as the correspondence between the estimated layers, which you see an example of here, and then the actual underlying histological layers. So the idea is like if the blue line here corresponds to layer 4 in this part of the RI, you want that to be consistent across the entire RI, such that when you average across the region, that you don't blur across the layers. And this layer positioning here, or that correspondence, is determined from your segmentation, and then also some algorithmic parameters in the way you're computing these layers. And so the way we try to get this correspondence, get accurate layer positioning, is by plotting the mean API profile of each slice across the RI as shown here. So this would be an example slice, right? Then we plot the profile. This could be slice 1, and it will look like this. And then we do that for all of the slices. And in all of them, we basically see the dip in the stria, but it's kind of messy here, right? Like you see that on the top up here, the dip is sort of shifted towards the deeper layers, and then down here it's shifted more towards the CSF. And so if we were to average across here, then we would blur the layers together. So I then use these plots here to slice by slice correct my segmentation until I landed on something like this, where we have a much better correspondence across the RI. And things becomes more consistent. And you can do that same exercise by plotting the profiles in the column direction. So instead of doing it through plane across slices, you get like a different dimension in plane. And then you just plot the profile per column, again, computed with Laney. And then you might, like, this is an actual empirical example. So you might start with something like this, and then you go column by column and adjust until you're happy with the consistency. And this turned out to be quite important at these resolutions, because we saw that in the inconsistent example that we don't see the peak, which is blurred away probably by the inconsistent averaging of layers. But then after being consistent, the middle layer peak does emerge. So this is to highlight that at these higher resolutions, we have very small room for error, and we really need to optimize our accuracy in order to see these fine scale layer features, which is also important at 0.8, obviously, but there's more room for error there. The second challenge is that of distortions. So again, when we move to higher fields and with the large, with the long readouts that follows from these high resolutions, we get more geometric distortion. And I try to illustrate that here by sort of outlining I'm highlighting the outline of one of our EPI images, which I call the forward EPI. So that's just one face encode direction, in this case, head foot. And then within that outline, I'm then showing the reverse EPI, so with the reverse face encode, and then you can clearly appreciate the distortion. And that can become a problem when you're trying to then align this distorted functional data to your high resolution anatomical scan, which is usually has very little distortions, at least in our case with the flash readout. And so to try to overcome that, we did distortion correction that has often been used at conventional layer fMRI studies, where it's the top-up approach, right? Where we use the reverse face encode scan to correct for the distortion. And then we see that actually at the global level, they seem to nicely match. So it did account for a lot of the global distortion problem. But then these blue arrows here point to regions of local residual distortions that were not corrected by this correction scheme. And what we then see is that when we try to align the anatomical to the EPI, it sort of fails in those specific regions where there was a lot of residual distortion left, even after distortion correction, and even after we use also nonlinear transforms to try and correct for the remaining distortions. On the other hand, when we look at regions that are more well behaved, where there's less residual distortion, and where we also have very nice contrast in the EPI image itself, then the alignment was super accurate, actually down to the level of the stria, which is highlighted down here by these black arrows. You can see that they nicely align between the EPI and the anatomical. So this this was a challenge in this particular study where we were kind of limited to those regions with less residual distortion, and so we could not really utilize the full field of view of our EPI acquisitions. But I do not think this is I do not think this is a deal breaker. Like, this is not something that I worry too much about. I think there are ways to get around it. Like, one potential solution that I think could be very good is to do distortion matched anatomicals that has been used quite a lot in many layer fMRI papers now, for example, advocated by Witzke van der Zwag. Another potential solution is to get shorter readouts, right, by higher acceleration factors or getting impulse gradients, which could help get us the shorter readouts that are needed to alleviate these distortions and alleviate this problem. The third challenge is that of is the motion correction, or the volume to volume alignment, and it's again related to the distortions, which we know are dynamic across an imaging session, right? So the subject moves and then the distortions also changes. And so we were considering if we should implement nonlinear transforms into the motion correction. But normally, I think almost every study just uses 6 rigid body alignments, right? So we looked into that here, and we tried to do nonlinear alignment across runs. So each profile here is the mean EPI profile of each run after alignment, either with both rigid and nonlinear transforms or rigid transforms only in this row. And what we saw is that in 3 of the 4 subjects, we did improve the alignment. So we quantified that by this RMS score here, root mean square error, which you can think of as the lower the value, the better the alignment across runs. And so in these 3 subjects, it did improve by using also nonlinear transforms. And in the last one, it was not significant, which may be also because this subject didn't have much movement to begin with. The RMS was already quite low. Then we also thought about doing nonlinear motion correction, like volume to volume and not just run to run. And so I show the results of that here, where again, this column now is using linear transforms only, and this is both rigid and nonlinear transforms. So this is one run where I just align all the volumes within that run to the first and then compute the activation map of that run. And we see that a lot of the activation that you can see after linear correction only is actually being suppressed in the case of where we also add nonlinear transforms, which you can also see here in the time courses. And this is an effect that Renzo has also described and talked about I saw it at least in a recent ISMRM presentation a few years ago, I think, where the explanation that he had was that if during activation blocks, there are these, like that, we see these signal fluctuations, right? Like our bolt response. And that can be confused by the motion correction, the local nonlinear correction. That activation can be confused with motion. Or those signal fluctuations can be confused with motion. And so the local specific corrections might wrongfully correct where it shouldn't have, which doesn't happen for the case of rigid only, because that's more like it's a global correction, right? And it won't do anything locally. So we refrain from doing nonlinear corrections within run, but across runs, it seems to help because like when we do the mean of a run to the mean of another run, there's no functional information there. And so we don't get this suppression effect. So this was the approach that we liked. We align all volumes within each run to the first of each run. And then we take the mean of all those runs and then align it non-linearly across runs. I hope that makes sense. That's the strategy we ended up using. And even though we were kind of left with doing only rigid body alignment within run, I was still quite happy with the result, and these potential dynamic distortions didn't seem to be a huge problem. So here I'm plotting the single volume profiles of different runs. So each plot is now a run, each profile is a single volume. And I'm doing that for all of the 4 subjects, where on the top row here, I'm showing the 2 runs with the least registration error. And down here, it's the 2 runs of each subject with the most registration error. And overall, I'm quite happy with the result. Like, it seems like the alignment is pretty good. And that's also corroborated by the motion videos. So this is an example. I think this should be this run here. So that's the worst run in the first subject, which is quite representative of what I see in general across most runs. So it looks like this. I hope you can see the video. But it to me nicely shows that motion doesn't seem to be a huge problem here, even at these resolutions and field strengths. I don't see too much residual motion going on. There are exceptions to this, though. So the 2 runs here highlighted by this green box are certainly very messy, but these are also characterized by a lot of motion. So this was about, like, in both of these runs, there were more than 2 millimeters of motion, which is extreme relative to the voxel size, right? And so these runs are probably better off being just discarded. And I think, again, I don't think motion is too much of a problem, even in this regime, until it is, right? Until the subject just moves too much, and then the rigid body registration doesn't work anymore, and that run is just corrupted and should probably be discarded. But I think these kinds of plots here, where we can utilize the features that we can see now in the mini PI profiles at higher resolution, I think those were very helpful to me to confirm that the alignment was to the accuracy that we wanted these resolutions, and also to flag runs where we were not happy with the quality. All right, so finally some takeaways and limitations, conclusions. So again, using non-gradient Yacoub API, previous studies have been able to resolve this activation at layer 4 and V1 to different degrees of clearness, I would say. Like, when you go at very high resolution, as in the fine Bergatron scan, then it's a nice and distinct peak. And then if it's at lower resolution, obviously this bump towards the middle will blur out. But I think the ability to resolve this, even using gradient Yacoub by pushing the resolution, is a nice methodological advance with at least 3 primary advantages, which is 1, a higher. So gradient Yacoub has superior readout efficiency, right? This facilitates larger coverage and higher temporal resolution, which is critical in neuroscientific applications. Then the second advantage is the limited spatial specificity of BOLD, which is its main downside. The sensitivity to these large veins is actually diminished precisely in this regime of ultra-high field and resolution. So the factors that we need to overcome the partial voluming effects that we need to push towards the single layers, the ultimate goal, those also help and have like a nice symbiotic effect with the spatial specificity of BOLD, which I find quite neat. And then also the higher CNR of BOLD can help facilitate even further spatial resolution gains that we need to push further, right? Then another point is, I think it's important that we start utilizing these lamella landmarks more, especially once we want to get at single layers eventually. So this has been done quite a lot for the Stria Genari in V1. There are many examples of that, and Renzo has also a nice example in M1 where he used 0.35 millimeter star weighted anatomical acquisitions to differentiate the layers, layer 5A and layer 5B in M1. but we obviously need to also be able to do this outside of those primary regions, and for more layers. And ideally, we would be able to do this directly in API space, to also get these extra advantages that we can use the features in the profile to achieve better layer positioning, more accurate alignment, and so on. So yeah, we see these results as a step towards doing true laminar fMRI, but obviously we need still higher resolution. So we are now looking at layer 4 in V1, which is a relatively thick layer, and it's a very well-behaved region, so on and so forth. And if we want to be able to do this for thinner layers and also in other brain regions, then we need to keep pushing the resolution. Then finally, I wanted to highlight what I see as the main limitation right now for our further push towards even higher resolutions, which is these long readouts that are needed with the large matrix sizes that we have in this resolution regime. And that's kind of the common denominator for three main limitations. So first of all, we have the limited field of view and temporal resolution. Ideally, of course, we want full brain and we want sub-second PR, so we can also do event-related designs. Now we're limited to block designs. Then there's T2 star blurring. So again, because of the long readouts, we have blurring along the phase encode direction, and the effective resolution is therefore lower than the 0.35 isotropic nominal value. And then also the long readouts is also the cause of those distortions that gave us problems with alignment. And so I think being able to overcome this, getting shorter readouts, again, impulse gradients would be great. And also, like, for example, higher density receive elements, right? Being able to do more acceleration is like these kinds of advances is something that I'm excited about and think is what we need to get us to the next level. So yeah, with that, thank you for your attention, and thanks to everyone involved in the project, especially the co-authors that are listed here. Thanks.
Thanks a lot, Lasse. Those were very high resolution data. Yeah, congrats.
Thanks.
I also find this kind of layer-informed segmentation interesting and something I want to play with. Specifically also because it's coming from different data, right? Different than what who was it? Was it Peter Koch or was doing before, of using the EPI data themselves in the informing the segmentation. Are there any questions right now already? Otherwise, I would start.
I will make the code for this public, by the way. So, for example, the code I'm using to, not that it's too complicated, but it's going to be out there, and so if you're interested, you can go ahead and use it. Yeah.
So basically, you're saying that you have a code that takes a column, then finds the minimum somewhere in the center, and then shifts your segmentation in that column. So
that would be cool. That would be cool. That's not what it does. It's much more low level than that. So I'm just plotting the profiles of each column or each slice, and then I'm using that to correct manually. So then I can go, okay, it's this slice is the problem. Then I go and correct that slice. Okay. But that would be a better idea, yeah.
And
we have a question from Abbas.
Yes, thank you so much for the talk. And I'm sorry, my question is probably very low level because I don't understand many of the things you said, but specifically about this layer-specific profiling and finding the minima as corresponding to layer 4, is that a universal feature or is that just more a visual area kind of a thing? Because I was wondering, the reason I ask is if I understand the whole thing that you're trying to present is once you basically have higher field, you can get higher SNR, better resolution, but then there is all the problem of things moving around, even though you can maybe get away with that, all those pile kind of veins kind of draining out. So there's so many good things, but then there's that question. So then I guess you somehow propose by looking at this profile thingy where we kind of expect this, we can go in and align things up. Anyways, if I understand all that. So how universal is that? Or how good should we have some information about the profile, the layer profile?
Right.
Yeah.
Gotcha. Thanks for the question.
Sure.
So definitely the feature of the stria that we are using here, that dip in V1, that's V1 specific. The stria of Gennaro is only in V1. But like for example, the example that I show here at the end, like you can get something akin to that in M1 in this case, right? So there you can also find special features in your, for example, T2 star weighted profile that lets you know which layer are you looking at. So when you see a functional peak, what is the underlying histological layer? How much that generalizes also to other regions outside of V1, M1, I'm not quite sure. And I'm not sure there's a lot of data on that. There might be that I'm just not aware of. But so in V1, this is a very well-known feature, and in M1, I think Renzo he relied on ex vivo scans and some histological knowledge that let him know that okay, when he see these dips here, that corresponds to this and that layer, and I'm advocating that we need something like this also in regions outside M1 and V1, and there are these there are, what is the name? Bands of, I'm not sure about the pronunciation. I think it's bands of bilager, which are these like the external band of bilager. That is the stria in V1, but there's also an internal band, which is, I believe, in layer 5. And so that might be another feature that we can eventually get at if we by keep pushing the resolution.
I see. Thank you very much.
Did that answer the question?
Yeah. Because I'm looking at some of the literature where people are looking at feed-forward, feedback kind of relations and how different layer profiles are affected by that. It seems in those ones, of course, it's a bit more complicated, and
Right.
people don't exactly know what to. I mean, sometimes they know, of course. Sometimes it's a bit. People want to study that. So that's why I wanted to know if we're looking at another area and we are not maybe so sure, or maybe we are, I don't know, about these. Is there a way around it, or it's still, open for? But anyways, yeah, this is really good. Thank you.
Thank you.
We do have another question also about extrapolating this to other cortical areas from Sylvia. Sylvia, do you want to unmute, or should I read it? We have
it was the same question. Thank you.
Okay.
We don't see any kind of anatomical features that can help us, so we're in the Wild West.
Can I ask Sylvia, what resolutions have you been
We're
looking at?
right
Because
now
I'm also curious.
We tried 0.65 and the SNR was just too low in prefrontal, so we're back at 0.85, sadly.
Right. Yeah, I think 0.65, it's also going to be hard, and I think even the stria of Gennaro would be hard to see at that resolution. So I've been done quite a lot of 0.5 also in V1, where you can sometimes see it a little bit in some particular regions, but it's kind of faint, and then you really need to go higher than 0.5 to clearly see it along the entire cortical ribbon of V1.
Yeah,
So,
thank you.
Yeah.
Maybe I would like to ask you about the variance of these layer profiles. Like you showed how stable they are across participants and across runs and so on. I'm also interested in the variance across different patches, like the columns or the columnar collections. How consistent do you see the bump? Do you see maybe sometimes even kind of negative signals in the surface, or specifically also having the multi-echo GRE? It's good at seeing the layers, the stria, but it's also even better to see the vessels, right? Even the diving vessels, yeah. So I was wondering about the kind of consistency of these layers across the cortical ribbon.
Right. Yeah, that's a good question. So I haven't looked much into I've just I find a region, the target representation of V1 in a region where we can see the stria in the EPIs and in the anatomical, and where we had where it was well behaved, we could get a nice alignment and so on, right? So we were kind of limited to smallish regions. And so I've just been looking at the profile within those entire RRIs, but in principle, like these, so the plots that I show here, the column specific plots, those are from the mean EPI profiles only, right? I guess we could plot the functional profiles of each individual column as well, and then look more into that question. But I haven't done that at this point. But if I do in the near future, I'll let you know.
If nobody else wants, I have a couple more questions. Maybe one, I would like to come back to this discussion on the blooming effect, like the dipole, and like from this Kamil Uluda models, like 15 years ago, kind of he predicted how much we have extravascular and intravascular bolt across field strengths. And I remember at about 7 Tesla, it's about 90% of the gradient echo bolt signal at the echo time of the T2 star should be coming from kind of extravascular signals of large vessels. So you're saying that as we go to different resolutions and also different field strengths, this is changing. And I would like to get a sense of how much we expect there. I know you said it's kind of a mixture of both in your experiments, and I guess the blooming effect will get worse as you go to higher field strengths, because this kind of surrounding pattern that you showed will have more of these phase jumps. But then as the resolutions are less, you're kind of overcompensating that effect. But do you have a feel of kind of how much? I'm sure you did 0.8 at 10.5 as well, and could compare those. Or I guess you could also try to do 0.35 at 70 and kind of tease this apart. And
yeah. To be honest, we haven't done that yet. Like we don't have these. Like, at least I don't have a direct comparison where I can compare like within the same field strength, but then the two different resolutions. So I don't have a feel about what is the relative contribution of these effects. Yeah, so that's hard for me to quantify, but I think now at these resolutions, I think we can suppress a lot of some of the extravascular contributions from the largest of the peer range, right? Those that are like, I think the largest are around like 500 microns and maybe a little smaller than that. But then there will still be a lot of PL veins also that we are not suppressing right now from the resolution effect, and where the field strength effect is probably more dominant. But like we need more data and more experiments to better tease apart the relative contribution. Yeah.
And then also there are the kind of intracortical veins as well.
Exactly. I think the thickest ones of those, the ascending draining veins, is maybe that's only at the upper part where they're thicker, but that's around 100 microns. So we also discussed that in the paper, like eventually maybe not only can we see them probably in our functional scans and maybe segment them out, but maybe we also start becoming just insensitive to them with through this effect once we really like there's still some way to go there in terms of resolution, but yeah.
We have 3 more minutes, and I do have at least one more question, if you don't mind.
Sure. Go ahead.
So you discussed these challenges, and you kind of boiled them down to the long acquisition duration, right? The distortions, the T2 star blurring, and also then the distortion comes along with the entire tail of other issues of the motion correction. So getting the readout short would benefit a lot. And you mentioned the impulse there. So I think right now you mentioned that the TR, like the shot-to-shot variance or the readout duration, is in the range of 115 milliseconds or so. So that's a long time, right? There's a lot of decay and a lot of phase error accumulation during an EPI that long, specifically at 10.5. So now with the impulse, you can shorten that. And then Kamil announced that you're going to have it in like within the next year or so. Do you already know kind of how much you can shorten it? Is it something then to get in the range of your T2 star, or would you still need other approaches on top of that, maybe segmentation or something like that?
That's a great question, and I have no idea. I don't have the numbers there. I don't know if maybe Luca or Nils, if they're in the audience, if they can help me out there.
Yeah,
I don't know how much to expect.
should be able to cut the readout to half. So it'd be good maybe for this coverage that we're using right now for 40 slices, but if we want to go for larger slices, we'll still need to do some in-plane segmentation. So we're waiting for you, Renzo. You know, we can get it to work.
All right, so we are at 11 a.m. So I want to thank everybody. Thanks, Lasse. And I'll see you again in 2 weeks. In 2 weeks, we will have the rehearsal presentation for ISMREM from myself and from Alessandro Pizzuti. Thanks a lot.